Alright guys, so first of all, apologies for not being online for a long time. Secondly, look at this light. Due to lack of use, my lightboard LED, the white one, went kaput. So I'm using some halo light and I look like I'm an angel or something, which may or not be because of the video. I apologize for the bad lighting. I'm gonna order a new LED strip, but we gotta work with what we have. So let's talk about separation, or separable equations rather. So let's start with that. You see, I'm invisible now. Separable equations. I'm not even sure that I got all that into the screen. Oh well, amateur hours today, but hang on with me. So this is going to be used whenever you have differential equations of the form y prime. I'm going to assume y depends on x, of the form f of x times g of x, where f and I guess that would not do much other than integrate with respect to x. I meant g over y. Alright, so with something like this, what happens is you can write this as dy over dx. You can divide both sides of the equation by g of x, g of y. I insist on x apparently. And then get here f of x. And so then what you can do is you can integrate both sides of this equation with respect to x. And so what's going to happen is this right here is just dy by the chain rule of differentials. So what ends up happening is that I can integrate this and I get the integral of dy over g of y. So I can integrate this. Well, you know there are going to be some functions where you don't know how to find the antiderivative, or the antiderivative just does not exist. But even if you have to leave these integrals indicated, you are able to solve. So let's do a few examples of this type of equation and see what kind of integrals we get. We're going to try to do one where we do separable equations is what we're talking about. Well, I'm going to try to do one where we do partial fractions, and possibly one where we do some integration by parts, just so we start practicing our techniques of integration. So I'm going to erase this, and I want to go ahead and get started with some examples. All right, let's start with a simple one. And so something of the form, a function of x, which we can think about as x sine of x, and a function of y that you can think about as 1 over y. So what I'm going to do is I'm going to separate the variables, and I'm going to multiply both sides of the equation by y. So this was very straightforward. Sometimes the algebra will be a little bit more exciting, if you will. Let me change these markers so it's starting to look a little bit not as bright. And so we integrate both sides. Now this one, again, integrate with respect to x, dy dx will give me a dy. And then this one is going to give me the integral of x sine x, that I intentionally put something that will necessitate for us to do an integration by parts. So I'm going to go ahead and do that here. I'm going to grab u as x, because that's written on the screen. It's very borderline, so I'm going to keep writing down below. And then dv, I'm going to write it as sine of x. Then dx, of course. And then v is going to end up being the negative cosine of x. And then du is going to be dx. So plugging this here, I'm going to have u v, which is going to be negative x cosine x, minus the integral of v, which is going to be plus that negative, cosine, and then dx, which is your v du. And then you integrate here, you're going to get the sine. And so, can I fit it there? Maybe not. So I'm going to erase and I'm going to write the solution. So copying everything, I get y squared over 2 equals the negative x cosine x plus sine x and plus c. And then you can solve for c and leave just everything as a function of x and y equals c to mimic a level curve, or you can just leave it like that, and that would be good enough. So that's our first example. Let's go ahead and look at some other examples, maybe 2 or 3 more, and just separating variables. This is probably the easiest, or one of the easiest differential equations we will encounter. But it's good to get started here. Then we're going to move on to the linear differential equations, where we will talk about the integrating factor. So let's erase here and do another example. All right, so let's take a look at this one, and so we'll do the same trick. So we're going to do dy dx, still separable. You have a function of y times a function of x, divide both sides by the function of y. And I wrote this one specifically so we get a partial fractions. As I said, I wanted to do a couple of techniques of integration so you get or start practicing them. So you start refreshing the knowledge from Calc 2. We did something very similar in class, so I don't think this one will be too complicated. So integrate both sides with respect to x. Know that this one changes into dy. So right hand side is quite simple. That's what you hope I write all the functions like this for your exam. So we integrate that. Now this one right here, we will have to rewrite as something of the form a y minus 1 plus b y minus 2 dy. So we have to do our partial fractions to get these coefficients, and as I did in class, I did the Heaviside method. So where you would notice that it only works for linear terms, remember that, be careful with that. So this term is made 0 by plugging y equals to 1, so we grab this entire term, so 1 over y minus 1 times y plus 2. You ignore that term that makes 0 when y is equal to 1, so you eliminate that factor. Oops. Yeah, I have special effect sounds there. And you evaluate that at y equals to -1. And I ran out of space there. So you evaluate it at y equals to 1 rather, which is the term that makes this 0. So when y is 1, this becomes 0. So I plug it into this whole term, but ignoring this term. So it's just 1 over y plus 2, evaluated at y equals to 1, I get 1 over 3. So a is going to be 1/3. And then plus, now to evaluate b, what I'm going to do, I'm going to grab this whole expression, but in this particular case, I'm going to just grab y minus 1. I ignore the term that gives me 0 in here for y equals to -2, and I evaluate this at y equals to -2. Now that I eliminated that 0 in the denominator, that's equivalent to setting your partial fractions and solving like you normally would, but this is much faster. So when you plug -2, you get -1/3 for this one, so plus negative, let's make it just negative. So minus 1/3, and then 1 over y minus 2 dy. And that's going to still be equal to x cubed plus 3 plus c. And then all we have to do here is evaluate our integral. I'm going to erase here and rewrite it, so I'll be right back. All right, I want to squeeze my answer right here. Man, not making videos in so long has me completely out of practice, but now I can integrate. So 1/3 natural log of y minus 1 for this one, minus 1/3 natural log of the absolute value of y minus 2 equals to this x cubed over 3 plus c, and I should have erased this, so I'll be right back. So let's write that. And then I will continue to erase the rest, and I'm going to simplify this one because it looks a lot nicer if I work a little bit on it. So let me go ahead and erase this, and I'll be right back. Alright, so the reason why I'm going to work on this one a little bit is because I have the cubes, the 1/3, which are going to become cubic roots. So I'm going to turn this into the following. The y minus 1 appears with a positive exponent, so I'm going to put y minus 1. Now this one appears with a negative, so I put it below, y minus 2. everything to the power of 1/3. Let's add one extra parenthesis because sometimes people don't like putting the 1/3 outside. And then we get x cubed over 3. But then this one is kind of nice if we just exponentiate the whole thing, both sides of the equation, and then we get that the cubic root of, I could then raise it to the power of 3, which would then be nicer. Let's then not do, well, let's write it now, whatever. So y minus 1, I'm fighting with myself, you notice that? Oh well. Exponentiating both sides, this plus c will become a k, and then e to x cubed over 3. I did this in class, but basically what I'm doing is writing it as x to the x cubed over 3 plus c, and then I write it as e to the c multiplied, and then I change that e to the c for a k. Now again, I can cube things out, and I can write this as y minus 1 over, I don't know if I have space, y minus 2, and then I cube it, I get k cubed. I'm going to keep naming it k because it's a constant, so it's going to get absorbed. When I cube this one, I just get a e to the x cubed, which is a lot nicer, I think. And I think I would leave the equation here, even though, because it's linear on y, you can multiply, collect all the common terms that have y and the ones that don't, and then solve it explicitly for y. So this is one that you actually can solve explicitly. But I ran out of space and the video is getting long. I have this thing that is extremely hot, and so if you see that the brilliance of my brain is coming through the forehead, it's not really that, it's just sweat. So I want to stop the video right there, and I'll see you in the next one. Thank you for watching.